Greetings, my name is Georgi Stoychev, and I would like to tell you a little bit about the X2C method, which is a new way of treating relativistic effects in ORCA6. Relativity is responsible for the color of gold, the melting point of mercury, the voltage of lead-acid batteries, and other important observable effects, and it gets more and more important as we go down the periodic table. Relativistic effects can be divided into two main groups: scalar relativistic effects that are mostly responsible for the contraction of electron shells around heavy nuclei, and spin-orbit coupling, which describes the interaction of the orbital angular momentum and the electron spin, and that is responsible for splitting degenerate energy levels depending on their total angular momentum quantum number. The easiest way to take care of relativistic effects is to use effective core potentials, or ECPs, where one simply replaces the core electrons, which are most susceptible to relativistic effects, by an effective potential. And therefore, relativistic treatment is no longer needed for the valence electrons, which makes this approach particularly cheap because we've removed some electrons and basis functions from the calculation. But we also cannot use this to compute properties that explicitly depend on these core electrons because they're gone. For example, hyperfine couplings or NMR properties or excitations from these core levels as observed in X-ray and so on. In those cases, we need to turn to relativistic theories. In non-relativistic calculations, we start from the Schrödinger equation, where we have a non-relativistic Hamiltonian that contains a potential and kinetic component that operate on a wave function, and that gives us the non-relativistic energy. In contrast, in relativistic theories, we start from the Dirac equation, which contains a different operator that has these 4x4 matrices, or 2x2 if we use this representation of the Pauli spin matrices. And that acts on a wave function that is now a 4-spinor, or a 4-component wave function, that can also be divided into a 2x2 or 2-component large component and small component that describe the electronic and positronic states. Now, there are technical difficulties in solving this equation, and also in chemistry, we're usually only interested in the electrons. So it is useful to think about decoupling the electronic and positronic states. And that is called a Foldy-Witthausen transformation, whereby we apply a unitary transformation to the operator, and that gives us a block diagonal form where we have now an operator for the electronic or positive energy states, hence the plus, and an operator that only acts on the positronic states. This decoupling transformation is exact in X2C, which stands for exact two-component methods, and it is approximate in Zora and finite order DKH. But in both cases, if we could do this for the full Hamiltonian, then we would first have to solve the full Dirac equation, which defeats the purpose. So usually it's performed for a model Hamiltonian, such as the one-electron Hamiltonian, or using a mean field operator for the two-electron terms. In the specific case of the X2C method, we start from the one-electron Dirac equation in matrix form, which is a 4-component equation. These matrices are all 2x2. So this is the matrix form of the operator. Then we have the solution coefficients, the relativistic metric, and the solution energies for the electrons and the positrons. Then we perform the unitary decoupling transformation that brings us down to a 2x2 block diagonal form, where the unitary transformation matrix is expressed like this, where X is a decoupling transformation matrix and R is the renormalization matrix. And finally, the X2C Hamiltonian takes this form, where we use L for the part in brackets. Now, as I said, all of these matrices are 2x2. However, only the matrix W has off-diagonal blocks. And these are the terms that depend on the Pauli spin matrix. But if we ignore the spin-dependent terms, we can obtain a block diagonal form for this, and that gives us the spin-free or scalar relativistic approximation. And then we get an effective one-component equation. ORCA6 is still limited to one-component methods. So even though we have X2C, it is effectively a one-component method. So we're limited to scalar relativistic effects. Now, the X2C transformation does involve operations with matrices that are twice or 4 times the dimension of the basis. So an approximation was devised recently called the diagonal local approximation to the unitary transformation matrix, or DLU, whereby the decoupling and renormalization matrices are approximated as direct sums of atomic blocks, and therefore we obtain the diagonal atomic blocks of the Hamiltonian via independent transformations, but still in the presence of the full molecular potential, whereas off-diagonal blocks are approximated using these expressions and the atomic blocks of the unitary transformation matrix. This reduces the size of the matrix operations to the size of atomic blocks, and therefore it reduces the computational cost of these transformations with what has been consistently shown to be negligible errors. And finally, turning to property calculations, usually property operators are expressed as derivatives of the Hamiltonian, and in the case of relativistic properties, we need to take the derivatives from the relativistic Hamiltonian. And this change of the operator is called a picture change effect, and it's particularly important for magnetic properties or other core electron dependent properties, and not so much for electric valence properties. Now, taking derivatives of the X2C Hamiltonian is fairly straightforward, although the equations do get a bit long, so I'll abbreviate them here. I wanted to point out that they do contain terms that are due to the derivatives of the renormalization and decoupling matrices, but they are often small, so they are optional in ORCA only for picture change equals 2. Similarly, for second derivatives, we have those contributions from first and second derivatives, and they are optional, but also we have contributions from first derivatives of the integrals, and these intermediate quantities are kept on disk, and that is governed by a variable called storage level. That is all the equations I wanted to show you. Now, a few words about what is actually implemented in ORCA and how to use it. Looking at the table in the right here, we can see what was available in ORCA 5. We only have the DKH and Zora approaches. We could compute the energy, but for optimizations or frequencies where we need the gradient and Hessian, we didn't have picture change corrections, so we had to use the so-called one-center approximation, where we used the decoupling transformation on the isolated atoms. We also have EPR properties, but we didn't really have NMR properties except for the NMR shieldings with Zora, which tended to be quite numerically unstable. We also had no picture change corrections for electric properties, although those are not very large. Now in ORCA6 with X2C, we practically have all of these properties, where for the G-tensor, we only have picture change corrections for the paramagnetic spin orbit term, which is the leading contribution. But we do have picture change corrections for the gradient and Hessian, and that is important, and I will show you in a bit. Now the calculation usually proceeds as follows. After the initial startup, we have the ORCA rel module, which performs the X2C transformation and stores the effective Hamiltonian on disk, as well as some intermediates. Then we solve the SCF or CAS-SCF problem. Then we go into the new ORCA prop int program, which computes the property integrals, and that already does the X2C transformation and stores them with the picture change corrections on disk. Therefore, any other module that uses them doesn't need to take care of this. The integrals are already relativistically corrected. We also store some intermediates here in case second derivatives are needed. We may need to solve the CP-SCF equations here if second derivative properties are requested. And finally, the ORCA prop program computes the actual properties, and it also performs the X2C transformation for second derivatives using those intermediates from disk. Now, turning to a few of the new things that are available. First, we take a look at the gradient, and then we take a look at some NMR properties. Now, I've taken this iridium complex and optimized it with various approaches and compared to experimental gas phase data. First, we have the non-relativistic calculation, where you see that the bond lengths are quite long between the iridium and the carbon and the iridium and nitrogen here. And the full X2C approach does reduce those bond lengths. Now, the disagreement here may be partially due to the arbitrary choice of functional here. But also you can see that the ECP does a very good job at reproducing those bond lengths, which is why we recommend ECPs for optimization. However, the one-center approximation completely fails. This optimization crashed, but it was going towards nuclear fusion. I will come back to that in the next slide. But first, I wanted to take a look at the different approximations that are available for X2C. First, we have the DLU approximation, and you can see that that introduces very small errors. And we also have an approximation where we neglect the response of the unitary transformation matrix, marked U0 here, and that introduces no additional error in the DLU case and a very small error in the full X2C case. However, looking at the timings, the time for the one electron gradient is negligible in the non-relativistic case. However, it becomes dominant in the full X2C case. Using the DLU approximation, we reduce that by an order of magnitude, and then ignoring the response of the unitary transformation matrix, we reduce that even further with very small errors. Coming back to the one-center approximation, we have noticed in the past that the one-center approximation leads to failure in the optimizations sometimes. And looking at this toy system with bismuth, you can see that the potential energy surface with the one-center approximation is completely different from the full DKH potential energy surface, which is why the optimization might get you to a different minimum or not converge at all, which is often the case. It usually affects DKH and also X2C, but not so much Zora. But this is why it's important that we now have the full gradient for X2C. But of course, using ECPs is once again completely okay in most cases. Now, turning to NMR properties, I wanted to point out in which cases the scalar relativistic approach is suitable. For spin-spin couplings, this works well when the Fermi contact is the dominant term, which is usually the case. But when the paramagnetic spin-orbit term becomes large, those are also the cases where the spin-orbit contributions are large in the relativistic theories. But for this example, both the scalar relativistic and spin-orbit X2C, these are not results from ORCA, agree well with the experiment, whereas the non-relativistic results don't. And for the NMR shieldings, scalar relativistic effects are suitable for the shieldings of heavy atoms themselves, where we have the heavy atom on heavy atom effect. For example, the xenon fluorides here. However, if we have a heavy atom on a light atom effect, these are usually dominated by spin-orbit coupling, and there our implementation is not going to work yet. Finally, a look at some inputs. Here I just wanted to point out that in addition to the keyword to select the X2C or DLU X2C Hamiltonian, you need to select a suitable basis set. Here we have the Weigand basis sets and auxiliary basis sets suitable for X2C. For optimizations and frequencies, we default to picture change 1, i.e. ignoring the response of the unitary transformation matrix. And for other properties, ORCA defaults to picture change 2. There is a warning in the output, so if you combine these two jobs, you need to pay attention, or you also could set this explicitly in the input. I just wanted to point out here that you could use a finite nucleus model, and that is actually very important for properties that have a Fermi contact-like term, like the EPR hyperfine couplings or the NMR J couplings. A few references for further reading. I just want to mention a nice review that I used when making this talk, and all of these papers that I used for the actual implementation. I would like to thank Yannick Franzke for all of his very thorough papers that I followed, and also for helping me debug the program, Ute Becker for helping with the parallelization, Frank Nese for entrusting this project to me. And most of this work was done while I was still at the MPI, so I would like to acknowledge funding from the Max Planck Society, but I am still maintaining this as a member of FACTS. And finally, I would like to thank you all for your attention.